All right, we have the sliding window median problem. Next, this is the problem statement. Essentially, you have an array of integers and they give you a window size k, and you're supposed to find the median every k windows. So you find the median here, and you find it over here, right? Next four elements, and you just keep moving till you get to the end of the array. That's all there is to this problem. The solution, though, is interesting because we are using a sliding window approach, and we're leveraging two heaps, just like the previous problem where we found the median in a data stream. The median is the middle value, right, in a set of values. So you have, when they're sorted, you have values bigger than the median and values smaller than the median. And the two heap pattern, you basically have a maximum heap for the values smaller than the median and a minimum heap for the values larger than the median. And you take the top values, the roots of those two values typically give you that median, right? The average of the two. If it's an even length data set, the average of the two values will give you the median. If it's an odd numbered data set, the top of the max heap will give you the median. Now, what makes this special is we have to, as we slide the window, we have to take numbers out. So we initialize these things. The small list, the large list is going to be heap. So this is a maximum heap. You can see the biggest value in this array of four items is on top. Next, you balance them, so make sure they're two apiece as necessary. Or basically the small list would have one item larger than the large list. We have a k of 4. We keep track of a balance to make sure everything across these two lists stays close to the same count. We have outgoing numbers, and you'll see what that's about. So when we make this first list, the first median is easy to get. You just take the average of the sum of these, of 1 and 2. The average of 1 and 2 is 1.5, basically. And that's the median. And you can notice the root of the heap. Now we're evaluating this, though. Next, we slide the window to... We have a problem. This question is hard. It's very formulaic, like a recipe. It feels like a cookbook. But I'll do my best. I'll try. Probably not my best. We come over with finding the median with two heaps. We come from the previous problem is a clear thing to do. It's an easy thing to do. But something is interesting. The way this balance behaves is kind of trippy. The way balance and outgoing numbers behave is a trippy thing. I mean, the median is standard, right? You see this small list, it basically is a maximum heap, and then your large list is the minimum heap that you're going to use to compute your median. So right after you divide it into, like, take 50% of this and put it in the large list. And I think it's worth showing the code at this point. Let's look at the code at this point. So we initialize things, the medians, we got that. Outgoing numbers, small list is a minimum heap, large list is a minimum heap as well. Although we do a trick to use a minimum heap as a maximum heap, you just multiply everything you're putting in there by -1. Yes, actually we're using the smallest. The smallest is the maximum heap, right? So we multiply everything we put in there by -1, and then when we transfer things from the small list to the large list, like we just did, we multiply them again to reverse their sign. So I think that's worth noticing. So we initialize everything, we push everything in the small list at first. Then we transfer the top 50% from the max heap to the minimum heap. Restore the sign. So this is how you do it. Interesting. You floor the k over 2 because you've seeded k elements in the heap, and you negate it and start off with a balance of 0. Start off with I equals k. I don't know. Do you use I anywhere? I see. Yeah. And then this loop does the heavy lifting, right? It does the heavy lifting. We find the median very quickly. You take your peak out of there, plus you peak out of here, and you multiply it by half. And is that because is k always an even number? Hold on, let me verify. All right, so k is not always even. Sometimes it's odd. So in this case, if it's odd, we use this bitwise operation to check if it's odd. And basically this returns 1 if it's odd. And we just take what's on top of this, the maximum heap. And of course, reverse the sign on it. Otherwise, we do the average, like so. Then, I think we are here, right? You do the average. That's where we are at. Now, if all elements have been processed, basically, we're setting I to k. So basically, the cursor that's moving through the whole list is already here. And if this was the end of the list, like get out of Dodge. Otherwise, we're starting to see what is going to be outgoing. So for the first thing, we're going to take 3 out of the list. So set it to outgoing number, then keep track of the incoming number. So in this case, 3 is outgoing and 0 is incoming. And we are essentially setting those here, incrementing I. So I has moved on from here to here. Now, if it's from the max heap, so if it's less than what's on top of the maximum heap, decrement less than or equal, decrement the balance, otherwise increment the balance. So this is interesting to me. You're shifting in balance. So it's possible for the balance to become negative after the first run, or positive by 1. And it seems to me like it never exceeds 1 or -1, but I could be wrong about that. Update the outgoing number in the hash map. So set it, increment. Okay, it can be more than 1 actually, because if it's already there, then it can be more than 1. Or set it to 1 if it doesn't exist, like we do here. So it's setting 3. It's seen 1 once. So this is a frequency map for the outgoing numbers. Sorry, I keep clicking that thing. So we take it out, and because it is bigger than 1, 3 is bigger than 1, we increment the balance, right? We decided here and increment the balance. And we add 0, because 0 is less than the biggest thing here. So we just add it over here. And so we have a balance of 2, because we had the first one here, and the second one from adding 0 to this list. Because it's bigger than 0, the balance is bigger than 0, we rebalance, we redistribute the numbers. We take the top thing out of here and add it here. So taking something out of the small list decrements the balance by 1. That's how we go from 2 to 0. And adding it decrements it by 1 as well, adding to the large list. So we went from 2 to 1 to 0. And I think you can see it here. If the incoming number is less than the top of the maximum heap, add it in that heap. Otherwise, add it to the minimum heap. Okay, we already discussed this. That was when we added 0 to the list. And then rebalance the heap. So it was greater than 0. It was at 2. So we popped a value from there and added it to the large list. Oh, actually, that's not what it's not this that ran twice that changed the balance to 0. Pardon me, I was wrong. It is this, basically, this line here. So it's been balanced. We reset the variable to 0. Okay, fair. This question is hard. If it comes up in an actual interview, the person is wicked. That's all I can say. And then next up, you calculate the median, take one out, add, bring 5 in, balance is changing, and it's bigger than 0, right? 5 is bigger than 0, so you move it to the large list. And then 1 is coming out. It is at the top of this list, so you always check whether it's at the top of either one of these lists when something is coming out. And so 1 is going out. 1 went out, actually. Yeah. Join outgoing number, but then it was here. So you pop it and remove it from there at the same time. And then you calculate the median, you update it. You just keep moving till you reach the end of the list. Increment the balance, add it to outgoing number. And you know you're going to take it out of here too. For 2. The new element in the window is 8. It's bigger than the largest thing here. We move it here, recommend the balance. Then two is outgoing, we took it out. And 3 is outgoing, we take it out again. And then finally we calculate the median once we're done. And with that process of eliminating things from the outgoing list, outgoing number key is here. That's what this piece does. Checks if it's in the outgoing number and doesn't. Okay, so that process doesn't balance anything. That final process does not balance anything. I hope this is as clear as mud. Because bruh, that's crazy. The only thing that alters the balance is not even the final step here when you're looking through everything in the list, but and removing them systematically based on whether they're on the top or not. It is this, not even this really. Is this here. Whenever we check if it's leaving the max heap or not, or we put something on the minimum and maximum heap, that's when we alter balance. Otherwise, we don't touch balance, like at the end, where we're trying to empty out the outgoing numbers array, numbers object. Yeah, not my best video, but it's a lot. Honestly, I don't want to re-record this. It's not worth it to me. Honestly, it's not a reasonable question if you ask me. It's in an interview setting, way too involved, my opinion. It's odd how someone probably got a PhD out of this, or like some huge award, and you're kind of expected to memorize all these things. I don't believe in that at all. I think you should go for a lot simpler problem, way simpler problem. Look at that, it's too much. It's just too much. Time complexity is another thing, right? Like, okay, so it's super complex, but it's like n log n. Well, see, the time complexity is hard to compute. Like, it's not a straightforward time complexity. I don't think it has any place in an interview question, personally. Maybe a coding competition, yeah, but like a technical interview, I don't think so. Some might say, what's the difference? There is a difference. The time spent in creating the heap, it's like asking a civil engineer, like a math Olympiad questions. It doesn't make any sense, right? Ask him civil engineering questions, please. The time spent in creating the heap is this. Okay, process elements in the loop. This, yada yada yada. Inside the loop, push pop elements from heap. that heap can grow. Worst case, the total time complexity of the algorithm is this. Okay, so we're pushing and popping. We're running through the loop. N minus k times. Inside, we push and pop elements from the heap. Okay, then n minus k in the worst case. Total time complexity is each of those summed up together. Because k is less than n or equal to n, in the worst case k is equal to n. So we have, for instance, the k is n here, we have log of 0, which is 1. And so it's a big O. These essentially evaluates to 1 times 0, right? Which is 0. So this is knocked out. So we just have k here, n and n. Okay, that's how they go, n log n. Look at that. Figure. As the size of the heap can grow to this, in the worst case, the space is this. The hash map is also this. So the space complexity is O of n. Okay. Okay. All right. That's about it. Thanks for watching. Too long.